Chapter 10 is a short chapter on rational numbers. It reviews addition, subtraction, multiplication, and division of all types of numbers, fractions, decimals. A rational number is actually any fraction, a over b. A and b can be any integer as long as b is not equal to 0, which is the symbol for b is not equal to 0. So here's some examples of rational numbers: 1 over 3, negative 2 over 6, 0.6 repeating, 0.71, and you can put negative signs in front of these. Those are all examples of rational numbers. So now we have a sort of a quick review of rational numbers. You're probably thinking, well, aren't all numbers rational? Isn't everything on the number line? You know, 0, 1, and everything in here, and everything this way. Isn't everything? Can't you write everything as a fraction? Well, sort of, but there are some things that are not rational. They're not rational because when you write them as a decimal, they either don't stop, they both don't stop, and they have no pattern. If you think about 4/10, you write it as a decimal, it just stops right there. Or maybe if it was this, 0.4 repeating, that would be a fraction that's equal to 4/9. So that has a pattern. If you take the pi, 3.14159, you could go another million digits and you don't have any kind of a pattern. Typical examples of numbers that are irrational are square roots of numbers that are not perfect squares. So if you enter in your calculator square root of 2 and hit equals, I can't be sure, but it comes up to be, I think it's 1.4 something, but then there are a whole bunch of other digits that come in there that have no pattern. If you put the square root of 9 in, you would get 3, so that's a whole number. So the square root of any number that's not a perfect square, like 2 or 5 or 8, will turn out to be an irrational number. But let's get back to rational numbers. In the next two slides, we're going to talk about the topic of equivalent forms of rational numbers. Let's think about negative 2 divided by 5, and what are some forms of that are the same as negative 2 divided by 5. You know that when you do 5 divided into negative 2, it could look like this. If you wanted to write it as a decimal number, you would get 0.4. But from what you remember about dividing a positive number into a negative number, the result is negative, so it would be negative 0 and 4/10, negative 4/10. Which, you know, is the same as 2/5 is 4/10, negative 2/5 would be negative 4/10. But what would happen if we made it a positive 2 and a negative 5? Would we get the same thing? Think about this model, negative 5 divided into positive 2, we would get 0.4 again, but it would still be negative because anytime the signs are different, when you divide, you get a negative number, which would also be the same as the opposite of 2/5. 2/5 being a positive number, the opposite of 2/5 would be a negative number. So in general, if you have a over b, and you make one of them be like the opposite of a, that's the same as a over the opposite of b, which is also the same as the opposite of a over b. I want to discuss an example that appears in the middle of page 214 under the topic equivalent forms of rational numbers. And suppose we start with an unknown number, we call it x, which is what's called in the example. If we double x, represented by 2x, and then take that result and divide by 3, that would be the same thing as starting with x and then multiplying it by 2/3. So, and if you just let's take a number like 6. Let x be 6. So 2 times 6 over 3. When you simplify that, you get 12 over 3. That's 4. I'm just going to prove that this works. If we take 2/3 of 6, we could write that as, make it 6 over 1 because we did the multiplication this way. 2/3 times 6 over 1, that would be 12 over 3, which is, again, 4. So there's proof that if you double a number, like start with 2x over 3, and it's the same as 2/3 of x. So that's one thing I want to take a look at, and then we'll take a look at another equivalent form of 2x divided by 3 in the next slide. Think of 2x divided by 3 as 2 times 1, which is this 2, multiplied by x divided by 3. And you can kind of see how this works, that if you do 2 times x, you get 2x, and 1 times 3 is 3. So it's kind of easier to go from this to this. But let's see where this leads us. We can change 2 over 1 to be 2, and put it in parentheses, and say that's the same as 2 times x over 3. Or you might write it this way, 2 times x divided by 3. So this is, let me just summarize it, the proof that 2x divided by 3 is the same as 2 times x divided by 3. And this is all under the topic of equivalent forms of rational numbers. And we're going to look at one more thing that we could say 2x divided by 3 is the same as. So I'm going to take back that last statement and say we're going to look at something that 2x divided by 3 is not equal to. You might kind of think that it looks good to say that 2x divided by 3 is the same as 2 over 3x. It's not. Let's think of 2/3 times x over 1, which we're just basically splitting this. We can do this. Split it apart, make this 2 over 3, make this x over 1. And it's true, let me write it out here, 2x divided by 3 does equal 2/3 times x over 1. But that's not the same as 2/3 times 1 over x. You can't just flip this to be 1 over x. This is not 2/3 divided by x over 1. If that was 2/3 divided by x over 1, then this would be true. And then this, of course, simplifies to be 2 over 1 over 3x, which is what we're saying here, that 2x divided by 3 is not the same as 2 divided by 3x. The idea of evaluating an expression is not a new idea, so I'm not going to spend much time on it. This happens if you have an expression such as 6x divided by 12, and you're told that x equals -8. So wherever you see an x here, you put in -8. So you just rewrite this as 6 times -8 divided by 12. And you do everything above the bar and everything below the bar. It's one way to look at it. And the bar separates things. It kind of groups things. Although you can actually, well, I'll do it this way first, and I'll show you a second way. 6 times -8 is -48. Divided by 12 is -4. I could have done also, there's 1 6 in 6, and there's 2 6s in 12. Then I could do 1 times -8 is -8, divided by 2 is -4. I could even do this, that 2 goes into 2 one time, and 2 goes into -8, -4 times. And then I have 1 times -4, and that's also -4.